Assalamualaikum warahmatullahi wabarakatuh. Today I want to do a lab presentation. So first of all, this presentation is presented by me, Muhammad Arif Hakimi bin Masri, and my metric number is 2410911150. In this lab, I explore the behavior and characteristic of the 741 operational amplifier through 5 different circuit configurations, which is the inverting amplifier, non-inverting amplifier, integrated, differentiated, and summing amplifier. The objective is understand the characteristic and behavior of the 741 operational amplifier, verify gain and output response for 5 op-amp configuration, compare calculate vs simulate output, and observe non-ideal effects such as clipping, offset, capacitor influence, and high frequency limitations. This is the key parameters for inverting circuit. This is the circuit for inverting amplifier, and this is the simulation for inverting amplifier. The output clip at 13.97 volt due to saturation because expected output is 30 volt exceed op-amp swing limit. Therefore, invert as expected 180 per shift. High gain makes the amplifier more sensitive to supply voltage limits. Demonstrate the trade-off between gain and linear output range. Non-inverting amplifier. This is the key parameters. This is the circuit for non-inverting amplifier. This is the simulation for non-inverting amplifier. The observed output is 10.96 volt, closely match the theoretical value. Clean, non-inverted output because of strong negative feedback. Small deviation due to input offset, finite open loop gain, and resistor tolerance. Shows good linearity when output stays within the op-amp's operational range. This is the key parameters for integrator. This is the circuit for integrator, and this is the simulation for integrator. Observed output is negative 1.12 volt, is close to expected small deviation. Select amplitude variation caused by input bias current, offset voltage, and capacity tolerance. Large feedback resistor prevents saturation or drift, keeping the output stable. Demonstrate the sensitivity of integrators to small DC offset, but compensation resistor and stable operations. This is the key parameters for differentiator. This is the circuit for differentiator. This is the simulation for differentiator. The observed output is negative 4.86 volt, is higher than expected. Differentiator amplifies rapid change in the input, so small spike or noise increase output amplitude. Finite bandwidth and limited slew rate also distort the waveform, demonstrate trade-off between sensitivity and stability. Differentiators naturally exaggerate high frequency content. This is the key parameters for summing amplifier. This is the circuit for summing amplifier, and this is the simulation for summing amplifier. The observed output is negative 5.98 volt, almost identical to expected. Output dominated by input with smaller input resistor 2 kilo ohm, higher gain, stronger contribution. Strong negative feedback result in excellent linearity, demonstrate the principle of superposition and weight sum. So we proceed with result and analysis. Theory vs simulation behavior is generally close, but deviation occur due to real device limitation model in LT space. The table shows the comparison between the expected output voltage and observed output voltage for all 5 experiment conducts. So this is the table for result and analysis. For example A, the expected value is 30 volt and the observed value is 13.97 volt. The observed value was too far from the expected value because LM741 op-amp operates on 15 volt supplies, but its actual value output is limited to only about 12 to 13 volt. The theoretical output of 30 volt exceeds this limit, causes saturation and clipping. This is a direct result of non-ideal output voltage swing. For example B, the expected value is 11 volt and the observed value is 10.97 volt. There's a small difference between expected and calculated value due to input offset voltage and finite open loop gain. Minimal loading effect and tolerance of resistance values also contribute. For experiment C, the expected value is negative 1 volt, while the observed value is negative 1.12 volt. There's a small deviation between expected and observed value because of minor input offset, small bias current, and component tolerance that slight integration of offset and non-ideal behavior. For experiment D, expected value is negative 1 volt and the observed value is negative 4.86 volt. Is a notable deviation because of amplification of high frequency content and noise dB per dt, which is limited slew rate and finite bandwidth executed tolerances. For example E, the expected value is negative 6 volt and the observed value is negative 5.98 volt. There's a very small deviation just maybe because of synthetic error, which is human error, that because of error of reading or error of taking a maximum peak value for reading. Trade-off and constraint identified. Op-amp saturation limit system performance. Integrates and differentiators are highly sensitive. Gain bandwidth products limit high frequency accuracy and ideal parameters affection precision. Practical design require feedback control. So we proceed with principle-based approach. So it's about how engineering principles justify the behavior of the circuit. Why the result appear as they do, how theoretical concepts connect to simulation outcomes. For principle 1, negative feedback controls gain. Op-amp gain is not from the amplifier itself but from the feedback network resistor. Changing R1 or R2 directly changes the output amplitude. The relationship holds in simulations. Principle 2, op-amp saturation and supply limits. Real op-amps cannot output beyond their supply range. LM741 output swing to 12 volt to 30 volt and 50 volt. For example, in everything amplifier, the calculated output is 30 volt while the simulated output cannot reach 30 volt. So the engineering principle that we use is output saturation and output limit by finite output swing. Principle 3, gain bandwidth product or GBW. Higher frequency equal to lower gain. For LM741, the GBW is 1 MHz. In the semi amplifier, output decrease at 3 kHz precious become more noticeable. High frequency cause the attenuation. This is the engineering principle for gain bandwidth products. For principle 4, superposition and weight summation. In semi amplifier, RF per R in. Input with smaller resistor has a bigger effect. Output is a weight and inverted combination of V1 and V2. Simulation makes theory to V2 dominates the output. A general principle that we use is superposition principle, which is each input added independently with its own gain. Principle 5, stability through capacitor. Capacitor controls slope, frequency response, and stability. For example, integrator use large resistor to prevent drift. Differentiator use 100 picofarad capacitor to control high frequency spike. Engineering principle that we use is frequency-dependent impedance of capacitor, which is essential for stabilizing high-gain circuits. For conclusion, the simulation of the inverting, non-inverting, and semi-amplifiers demonstrate strong agreement between theoretical gain calculation and actual LT-spice output. The result also highlight key non-ideal characteristics of the LM741, such as output clipping, bandwidth limitation, and the influence of resistor ratios on signal weighting. Overall, this lab successfully met its objective, improved my understanding of op-amp operation, feedback control, and practical amplifier performance in analog electronics. That's all from me. Thank you.